Hello, my name is Ignacio Cirac. I'm a scientist working on quantum physics at the Max Planck Institute of Quantum Optics in Munich, Germany. And on behalf of the Munich Quantum Valley and the Munich Center for Quantum Science and Technology, MCQST, I would like to welcome all the viewers to the second edition of the Munich Quantum Stammtisch. Abraham Paris, a Dutch physicist and scientific historian who regularly met Albert Einstein at Princeton, wrote in an article about him. We often discuss his notions on objective reality. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believe that the moon exists only when I look at it. The rest of the walk was devoted to a discussion of what a physicist should mean by the term to exist. At the time of this discussion, around 1950, quantum physics was being developed, and the interpretation of its intriguing laws was very much gave rise to many controversies. Now, 70 years later, we are surrounded by quantum physics, and many of the technological developments that we have around us are because of quantum physics. However, we're still asking ourselves the same questions about interpretation and quantum physics, and which are exemplified by the title of today's Quantum Stammtisch. Is the moon there when no one is looking? And to discuss this topic, we are fortunate to have with us selected scientists. We are tremendously grateful to all of them, as there are very few occasions where experts come together to speak to the general public about the foundations of quantum physics. I will briefly introduce them now, and I will not mention their outstanding contributions since it will take most of the time, but I just give some quotes, mostly taken from their websites. And nevertheless, I encourage you to look at the website of our Munich Quantum Valley, because you will see there some of the answers that they gave to this question. Is the moon there when nobody looks? Okay, so let's start with Alexia Auffèves. She is the head of quantum engineering and professor at the University of Grenoble. Her current research is focused on theoretical and quantum optics, solid-state physics, quantum thermodynamics, and quantum foundations. She says that quantum mechanics leads to redefine the characteristics of physical reality. I investigate this novel quantum ontology. The next guest is Časlav Brukner. He's director of the Institute of Quantum Optics and Quantum Information and professor at the University of Vienna. And he has in his website, after having devoted several years to the study of foundations of quantum theory and quantum information, the scientific interest of my group shifted towards the understanding of the interplay between quantum theory and gravity. The next one is our Bavarian colleague, professor of physics and the College of Science and Mathematics at the University of Massachusetts, Boston, Christopher Fuchs. And there are many quotes in his website, and just let me give you one. He says, this collection of letters, he has many things. I advise you to go there and to check them out. But he has a set of letters, and he says, this collection of letters traces my transition from taking the quantum state's essence as information or knowledge to being instead freely chosen Bayesian degrees of belief. And finally, to being nothing more than the pragmatic gambling commitments one endorses in any given instance. The next guest is Leah Henderson. She's professor at the Department of Philosophy, University of Groningen. And she says in her website, my primary research interests are in philosophy of science and epistemology. My goal is to contribute to a deeper understanding of some of the most fundamental features of science, but I'm also convinced that philosophy of science should be socially engaged. Consequently, my research program has both a theoretical and a more applied dimension. The next guest is Robert Speckens, faculty at Perimeter Institute of Theoretical Physics, and his research is focused upon identifying the conceptual innovations that distinguish quantum theories from classical theories and investigating their significance for axiomatization, interpretation, and implementation on various informational tasks. And the last but not least guest is Anton Zeilinger. He's president of the Austrian Academy of Sciences. He's professor at the University of Vienna and founder of IQOQI as well. And he's the only experimentalist that we have. And although, I mean, some of the other ones have been involved in experiments as well. But what an experimentalist. He's one of the best known scientists, especially for the first experimental demonstration of teleportation. That's what I think everybody knows. However, he has been one of the few people who realized more than 40 years ago that the deep questions posed by quantum physics could be investigated experimentally and would have potential applications in fundamental in research and some of the fundamental applications that we have, like in quantum computing and quantum communication, and we were born with him, basically. So welcome, everybody. And so it's my pleasure to have you here. And so just to launch the conversation, let me say that quantum physics, of course, is a very successful theory. We can describe with a high precision many experiments. We can understand what are we made of atoms, quarks, molecules, solids, etc., etc. However, as I mentioned before, if we really believe quantum mechanics, then we have to change a little bit our vision of reality, our vision of nature. So let me start just posing this question. So does quantum mechanics provide a complete description of reality? So who wants to start?
I can take a shot at it. No, it doesn't provide a complete description of reality. It does provide a set of tools that we can use for better swimming in this reality that we're in. So I would say if we look at quantum theory, it isn't an actual representation of what is in the world, but instead a set of tools for making decisions in that world. Now, that doesn't mean that it doesn't say anything at all about reality, because you can ask the question, why this set of tools rather than some other set of tools? And answering that question is an indirect way of saying reality must be shaped a certain way so that this is a good way to proceed in our interactions with the world.
So who wants to say something?
Which contrasts with Rob Specken's point of view.
All right, I'll jump in. So maybe if I could shift the question a little bit, does quantum theory describe reality? You could ask about different elements of the formalism and of quantum theory and say, for any given part of the theory, does that somehow changing that part correspond to changes of reality or not? So, a lot of the disagreements in the field of foundation of quantum theory is about whether the central object that we talk about in the theory, which is the quantum state, whether it describes reality. So if I imagine two different quantum states, am I imagining two different worlds? And so my view on that is no, that the quantum state is much better thought of as being a description of incomplete knowledge of reality. So it's more like the as Chris Fuchs likes to say, like the weather person's forecast that the probability of rain tomorrow is such and such. That's not a property of the weather tomorrow. That's just a description of the incomplete knowledge of the meteorologist. And so for a variety of reasons, it seems to me that's the best interpretation of the quantum state, that it's analogous to a description of incomplete knowledge. So in that sense, no.
Can I say something briefly? My answer is yes and no. I mean, it depends what you mean by complete. In my conviction, quantum physics is a complete description in the sense that it's not completable. I think that's it, and we have to live with it. Now, the question is, so in that sense, Einstein's dream to have a more complete description of reality beyond quantum mechanics will probably not go away, certainly not within a long period of time. Why do I say for a long period of time? Because some of the most intelligent members of the species Homo sapiens have worried about these questions and have not really come up with an answer what reality should be or what it is. Now, the question is, when we say incomplete, I said incompletable in a mathematical sense, so we probably can never add anything. But when you guys say incomplete, and the description with the weather is a very good description, do we really mean that there is something more complete behind, which we just can't describe? If so, what's the evidence? I don't see that we have any evidence for that, which also means that we have, I don't say that we have evidence that there's nothing behind, but this is one of the questions which are probably beyond our possibilities or whatever. Let me say what I believe in terms of what the quantum state is. And I here go very much along with the way I read my favorite philosopher, Nils Bohr, and also to some extent Heisenberg. My view is that all we really can talk about are features, I'm an experimentalist, features of the apparatus. So I go into the laboratory, I see a laser, I see some lenses, I see some things which we call detectors, I see a computer and whatever. Okay? And using all this information, I can construct a quantum state. And what is the quantum state good for? The quantum state is good for me being able to predict future experimental results, probabilistically, and so on and so on. Which simply means, what are experimental results? They are features of the classical world. So the quantum state connects a classical world apparatus, my knowledge of the past, with some possible knowledge of the future. And that's it. And I don't think there's no more. And also there's not more necessary. It works perfectly. We are happy with it. And let's go on.
I thought it was nice, Anton, that you channeled Wolfgang Pauli in a way with your slogan, which is very nice.
I channeled Wolfgang Pauli?
Yes, I think so. In a letter to
Pauli.
In a letter to Marcus Fierz that I once ran across, Pauli said to Fierz, "I believe that Einstein is right, that quantum mechanics is incomplete, but it cannot be completed," which is a lot like the slogan that you just said, that it's complete in the sense that it is incompletable. I thought that was very nice.
Okay, so
I'm curious whether anyone's going to say yes here. I'm not, by the way, but I think that's mostly just because I think it's actually more interesting to say no as an answer to this question, because I kind of agree with Anton that what the state gives you is sort of resources to make descriptions of what happens in particular situations, particular different ways that you might look at things, particular measurements that you might make. But it doesn't give you a sort of nice overall description, which is anything like what we're used to and what we normally would like to have. So that means that it's attractive then to think of the state as not just a direct, complete description of what there is, but to explore other ways of thinking about it, like the one that Chris mentioned.
Yeah, this is a good point. This I think, what Anton said and what you just said, Leah, is a good contrast between Rob and I. Rob and I come from the school of Bayesianism. But Rob, if I understand him correctly, wants to think that when you have a quantum state, you have incomplete knowledge. And there is the implication in that formulation that there's something better. There's something more to it. Whereas Anton and I, and maybe you, Leah, would say, if it's a state of knowledge, what is the state of knowledge about? What is the state of knowledge about is the experimental outcomes and not some further underlying reality.
Well, maybe I can. Oh, sorry. Go ahead, Alexia.
So yeah, because Leah asked who would agree on the fact that quantum mechanics is a complete description of reality, and I will say yes and only yes, not yes and no, not no. Leah, you said you think it's more interesting to say no because there is something more to explore, because you need to define what you should complete quantum mechanics with. But actually, I think that from the philosophical point of view, it's the other way around. It's interesting to consider quantum mechanics as something that is already complete and work out the philosophical definition of what a state is, taking into account, again, the fact that quantum mechanics is complete. So there is this dichotomy that some of you mentioned about is the quantum state a state of knowledge, of a state of reality? And I want to add another bit in the options about what a quantum state is. It could describe something which does not describe a system only, but a system and the experimental context around. So this is an approach that we are promoting with Philippe Grangier, with this objective contextuality. The fact that actually, when you talk about the quantum state, and then I'm going to reformulate something. Something I wanted to add is about the question that Ignacio asked. Is quantum mechanics a complete description of reality? And I think it also conveys another question, which is, what is reality? How should we talk about the description of reality without having defined reality in the first place? And the strategy that we have developed with Philippe and Naila Farouki, who is a philosopher for a few years now, is to start a redefinition of reality that is not based on any mathematical formalism. The idea is really to restart from a phenomenology of the experiment that quantum mechanics gives us. And the fact is that if you want to define reality, you define it with certainties. You define it with results of experiment that you can obtain repeatedly, that you can obtain at will. Whenever you want to check, you will get back the same result. And this allows you to say, okay, this is a good property of the stuff that I'm studying. And in which condition do you get this kind of certainty? It's which is sorry, I didn't drink anything. You get it if you don't change the experimental context, if you don't change the type of question you ask. That's why we are brought to define, in the spirit of Bohr, who was saying that reality is contextual, and the properties that we are going to obtain are contextual. So I think this is a third path. It's between the quantum state as a state of knowledge and the quantum state as a state of reality. The quantum state is something which is contextual. So, and in this view, quantum mechanics is complete.
Yeah, I mean, the thing that I find a bit uncomfortable about that, though, is that normally when you sort of want to say that you're confident that something's really there, one of the sort of most fundamental things that you do is check it across different contexts, check your predictions that they work out in different contexts. And so, I mean, that's one of the sort of main arguments for scientific realism in general. So I'm not so happy to sort of restrict things to context by context kind of reality, just for that reason. I'd rather think the way quantum mechanics stitches together the contexts has its own sort of consistency, and it makes sense. You can do things with it. It's just that it's not the usual stitching.
But I think it all depends on what, sorry, I just answer and then it all depends on what you mean by context, because this can be a notion that is not totally understood. Context, and especially again in the spirit of Bohr, it could have been understood as the experimental context. You know, when there is someone that built it with the precise aim to measure a system or to study a physical system. But context can have a much broader sense, and especially after the works of Zurek, context is the environment around the system, the environment that will be influenced in some way by the system and therefore carry an imprint on the system. But this environment will be affected in such a way that it will carry some classical state of matter that we will all be able to check at will. So I don't know if it answers your question, but it's further than operational. Context is not an operational concept. It's a classical environment that is influenced by the quantum physical system below.
So I would like to go back to this context-dependent reality, which is maybe a weaker notion of reality. But before that, what I hear from the participants that there is, well, kind of agreement that the quantum state is a representative of knowledge, or in terms of Erwin Schrödinger catalog of knowledge. But then there are these two, I think, important questions. One is information about what, and that's the point where we differ from each other. Is it information about some underlying real state or underlying reality or the real state of affair, or it's information about probabilities for future outcomes, what Anton suggested. But the other questions, I think it's also important, and it's the question, whose information? Is this somebody, do we need to assume the physical presence of an agent or an observer who will use this information eventually? Or we can think about that this information is something more than that. And what I mean with this refers to, for example, what Shimon Malin wrote once. What if an observer had a martini before observing? Is this the same information then? Or we feel like it shouldn't be dependent on these things. So can we say something about, without referring to the physical agents? And these are some kind of hard questions. And at least we can say that it's useful to think about fictitious observers. We don't need to excuse ourselves for that. We use this all the time. In thermodynamics, when we say that we cannot build up a perpetuum mobile of the first or second kind, we think about building up a machine by an agent. Or when we say that we cannot transmit information, we think about a protocol of communicating parties. Why should it be different in quantum mechanics? So I think it's a useful thing, but still there is a question that lurks behind is, can we speak about existence of this information without reference to the physical presence of agent or user of that? And this is again back to your maybe question for the whole evening. Is there a moon when nobody looks at it? Maybe just to add one question at the end, and I mean, my reference is to the question of Alexia, what she said, is it the state of reality and the state of information or knowledge? If Anton is correct, that quantum state cannot be complete, maybe there is no difference in these two questions. Maybe this is the same question.
Can I broaden Časlav's question? I mean, when we talk about quantum mechanics and quantum states, do we really need observers? I mean, in modern language, I think these are called agents or whatever, I don't know. But is that necessary? I don't know what people believe. I don't think so, actually. So if I have been interpreted in a different way, then I was imprecise. Like the quantum state, what you just said, Časlav. It's like in the two-slit experiment. The interference pattern doesn't show up as long as there is the possibility to obtain information about which path the particle took. And it doesn't matter whether anyone takes note of that information or not. So there is no observer necessary there. This is my personal opinion.
I mean,
in that sense,
yeah, and to go in the same direction, the notion of context allows getting rid actually of the notion of observer. I mean, it's the same idea that Anton just said. If you send the Max Zender on the moon, I mean, no one is here observing if the photon will go through this path or this path, and the result will be the same. So it's important to detach the agent actually from the description, and it's in the same direction as I was saying before to Leah, the fact that a context is not necessarily something intentional that we build to measure something and there is an agent to do the measurement. We don't need this. A natural refractive medium can measure a polarization, and no one was here to build it, and still the measurement takes place. So
yeah, I mean, I would say I think there's sort of two different reasons why you might want to keep an agent. So one is the one you're sort of, I think, referring to in a way, the measurement problem, right? The sort of where do you sort of begin and end when you're making a measurement? But the other reason you might think you might need an agent is because there's something a bit strange with quantum mechanics and the way it can't be sort of modeled straightforwardly by a sort of causal description. And so then you start to wonder what's going on there. And could it be that for some reason, the reason why you can't get the sort of normal causal description is because actually you've got some sort of other so I guess what I'm trying to say is that like you the difficulties that quantum mechanics has with things like Bell inequalities and so forth sort of point in the direction that there might be some sort of unusual notion of causation at work. And then we have to ask ourselves, well, where did we get our notion of causation from in the first place? And is that a sort of agent-dependent idea? And if we think that it is a sort of agent-dependent idea, then, and we've got, so that's where the sort of rub with quantum mechanics seems to be. And so I guess I'm not being terribly coherent here, but that's one reason why I think we maybe need to worry about the agent, keeping it in, that it can't just be taken out as a kind of context instead. Maybe someone else can say something and I'll try and formulate that a bit more.
I try to follow up just a little bit on what Leah said. I would love to have a book that said the emergence of decision theory rather than probability, but I don't have it at home with the pandemic going on. But imagine, if you would, that quantum theory is an extension of decision theory. And what I mean by decision theory is how to reason effectively in the light of some uncertainty around you. For instance, it might be financial markets, it might be medical testing, or it might be the consequences of taking some action on a physical system. So the experimentalist has some physical system and he builds his big equipment and the equipment takes actions and then it leads to consequences, it leads to outcomes. Suppose you took the point of view that what quantum theory was an extension of decision theory. So you pull out a book that has all the various rules of decision theory. It's, and in theorems and proofs, and then you put the book on your desk and you say, this book has all of the rules of decision theory in it. It helps us whenever we want to use it. So therefore, book, if you could speak to the book, make a decision. And the book doesn't do anything. And you try again. Book, make a decision. You are decision theory. Well, it can't. And the key reason is it's a manual that helps decision makers or helps agents. So that would be my reason or my explanation for why it's crucial to always have the agent in the picture of a quantum mechanical application. A similar joke would be if you had a Boy Scout manual that tells young men how to lead better lives. And it has all the Scout laws. A Scout is trustworthy, loyal, helpful, friendly, courteous, kind, obedient, cheerful, thrifty, brave, and clean, and reverent. And you put the manual on the table and say, Boy Scout book, go out and do a good deed, because that's one of your laws. The manual can't do a good deed, but the manual does teach young boys how to go do good deeds. That's it.
Maybe I can have a take on this. So this is an attempt to say that quantum theory comes out as a necessary tool to kind of go through this life and, based on our experiences, build up our beliefs and so on. And I think this is a very nice idea. But I feel that maybe it won't work. And the reason is that I don't see the difference between this classical and quantum decision theory. In other words, that we certainly, there is a decision theory that would be very applicable for classical-like theories, just like classical Bayesianism. And then there is a decision theory that will be very applicable for quantum world. And they are each individual and self-consistent. Now, why should I end up in one or not the other is the main question here. What is this non-trivial part that goes beyond decision theory that will tell me we have to end up in the structure as quantum theories and not in the classical one? So the decision theory is there maybe to give the meaning to probabilities as degrees of beliefs, but it doesn't seem to be the thing that will single out quantum theory. Or it has to be added something in that. And this that should be added is actually the most interesting part of the whole story.
I'm in 100% agreement with that. There are at least two possible worlds. One where the decision theory you should use is unadorned by quantum considerations, and another possible world where you use the calculus of quantum theory. And the most interesting question is exactly what Časlav just said. What more? What further assumptions are being made so that one is forced to the quantum calculus rather than the stuff in Ian Hacking's book, for instance? So yeah, I think you hit the nail on the head, Časlav.
I would like to add a question to Časlav one, which is why is there randomness in the first place, in your view? Because if you have a decision book, it means that you have to go through random events and make decisions in the middle of random events. So where does this randomness come from? That's a question to Chris.
Where does it come from? Where do elephants come from? Where do birds and bees come from? It's just a fact of life that we don't have certainty. So, yeah, so you might say,
no,
this is a fundamental assumption of quantum theory, that we have uncertainty and we can't overcome it. So now we try to make the best we can with it.
So it's a change of, okay. I would say it's a change of physical program, or a change of program for a physical theory.
Yeah, I would think so. You would characterize it that way. And I think Leah would characterize it as some offshoot of a philosophy called pragmatism. Maybe Rob would as well, from my discussions with them.
Yeah, if we would go back to the way pragmatists would build up a decision theory, probably from certain axioms about a particular agent's preferences and what makes an agent have coherent preferences and preferences which make sense. And I guess one of the interesting questions there is, do we need to modify those sort of constraints that we see on an agent and how they prefer things? Could a modification of that give you the quantum decision theory rather than the classical one that we're used to, where we get a kind of division into probabilities and utilities of a particular kind that we're kind of used to? So that's I think one sort of question you could ask.
But it seems that this goes then beyond mere idea of decision theory, these constraints.
Yes, absolutely. I would say decision theory plus something about the character of the world. So decision theory plus some ontological statement. But
you were never so ontological as today.
Oh,
where is the ontology? Where is the ontology here?
Rob, defend me, please. I've always said this.
So maybe just a second. So maybe it's getting too technical. I think that probably many of the viewers will not understand the conversation at the moment. So I want to go down to earth, and to bring up another topic which is related to the conversation that you had, but it was actually it was brought up by some of you already. Is that when I asked the question whether quantum mechanics is complete, everybody say yes or cannot be complete or things like that. But I mean, there are people who say that actually it's not. That there is a theory in which everything, I mean, the moon is there, exactly there at the position and the velocity whenever I don't look at it, and it's there, and it doesn't matter if I'm looking or not. These are these hidden variable theories. The only price that we probably have to pay is that these are non-local. And so maybe we can explain to the general public, so why a theory like that is realist, is like a theory that, well, everything is defined, there are not paradoxes of that kind. It's not so satisfactory to some of you. And because, so what is the problem with no locality, especially if it cannot be observed, if they will have no contradiction with experiments that we have?
Fine tuning. Rob, speak up on fine tuning.
Okay. And I'm going to try to answer your question by maybe tying into a few of the threads that came earlier. So first of all, I think from the conversation, it's clear that perhaps none of us think that observers play a role in quantum theory, like making reality, that we sort of create the reality of the moon. But I think that there is a question of separating out, what's about the observers and what's about reality. So there's this nice Jaynes quote, which I like, which is that, quantum theory is a peculiar mixture of elements that impart realities of nature, impart incomplete human information about nature, all scrambled up by Heisenberg and Bohr in a way that no one has yet seen how to unscramble. So to answer Anton's question, I think that there's sort of like when we do quantum theory, there's sort of talk about, what happens when you learn the outcome of measurement, and we, to some extent, the project is, can we sort of take out what's about just us and our knowledge, and what's about the reality. And so the biggest challenge to that, so like as you said, Ignacio, I mean, you could imagine that there's just some deeper reality that we have some knowledge about, so a little bit like Plato's cave, the prisoners see the shadows on the wall, but there's really some greater reality, like a three-dimensional object, and depending on how I orient it, I see different shadows. So there could be a kind of notion that there's some reality and we only have limited information about it, and the formalism of quantum theory is sort of a description of that limited information. But Bell's theorem is what shows that doesn't work, essentially, that if I imagine that there's some common cause explanation, for example, of an experiment where I have two measurement devices, two particles go off, get measured. Yet, I should say, to my mind, like the key thing about James's unscrambling, as Leah pointed out, is you want to distinguish causation from correlation. Correlation just means if I learn this, I can make inferences about that. Causation says if I manipulate this, I can come to change that. So in many cases we see correlations and we don't know how to explain them causally. So for any correlations that quantum theory predicts, there's a question. Like in the Bell experiment, we see correlations, and the question becomes, could I explain this as a common cause, and that's the correlation. So this would be like a more common example would be if you've seen correlations in medical data between people taking a drug and recovering. That doesn't necessarily imply that the drug caused the recovery. It could be that some certain types of people are more inclined to recover or more likely to recover than others, and they're also more inclined to go get this drug. And so then it would be a common cause explanation. So that's one of the questions about Bell, and the usual way of thinking about our knowledge of reality can't explain it with a common cause. So that leads people to say that, oh, there's this action at a distance. It must be a cause-effect relation from one wing to the other. And so then my main objection to those sorts of accounts, to answer your question, Ignacio, is that to make them work without innovating probability theory in the ways that we were discussing earlier, that Chris and Časlav were talking about, changing the sort of calculus of how we describe our knowledge. If you don't do that, then those explanations are fine-tuned explanations, meaning the way you explain the fact that we have this non-local action and yet we can't use it to send signals is by choosing very carefully the values of certain parameters in the model, which would be extremely unlikely. So just sort of crafting it very carefully to make that work. So that's the fine-tuning that Chris was mentioning. So I'm on the side of it makes more sense to think of this as a common cause, but to innovate our calculus for inference.
Can I say something?
Please, Anton.
I think this. I should say it to the general audience. I mean, you guys can disagree with me, but this discussion goes back to the way I see the debate between Einstein and Bohr. Nils Bohr, for the general audience, Nils Bohr was a famous Danish physicist who got the Nobel Prize for explaining the atom, at least in a certain way, which was then later on shown. Was later shown to be superseded by quantum mechanics. But anyway, for Einstein, the question is, does physics describe the world? Does physics describe reality out there? Whatever we mean by reality, but we have some notion about reality, or does it describe what we can say about reality? And that is in a nutshell the issue. I mean, for the people who listen here, and in my opinions, this question is only very weakly related to the question of non-locality. In Bell's theorem, which was mentioned, you have these two particles which are entangled, and you measure one, and that measurement result then modifies the quantum state on the other side without anything being signaled and so on. I would like to mention the Kochen-Specker theorem, which goes back to Specker. Specker was a very religious person. He was a preacher in some church in Zurich, and he was also a fantastic logician, one of the top logicians of his time. And he asked himself the following question: suppose one day you stand in front of God, and God has to decide whether your deeds were good or they were not good. Then God would have to know somehow what would have been the effects of what you did if you had done something different. And then Specker shows that for quantum systems, this is not possible. So for quantum systems, there are situations where you cannot have the answers to all possible questions which would be relevant for God to make the decision somehow existent. And this is, to me, this is a most important insight, in a sense that you have difficulties with the picture of reality, even without invoking spatial long distance and all this kind of thing. I just wanted to say this kind of as a background also to other people, so they know a little bit what we are discussing about.
This was very useful, Anton. I think that yes, and I guess that it connects to what Alexia was saying also at the beginning, right?
Right.
So maybe one can add one other negative, so to say, feature of this deterministic account of reality, like de Broglie-Bohm theories, there's non-local theories, is that really, as Rob was explaining, these are these two measurements that we say space-like separated, so they are very distant from each other. And then a causal explanation has a cause and effect. And it turns out that in these situations, if we would believe really that these observed correlations are produced by these non-local theories, then it seems that some observers in some reference frames would say, well, A causes B. Whereas if you move differently in another reference frame, it will B causes A. So at least what you can expect from some causal explanation, that you know for sure what is a cause and what is an effect, that there cannot be dependence on some reference frames. And so the consequences of that is that in these theories, you have to have a preferred reference frame. Everything is really happening in some very particular reference frame. And this really collides with some notion of relativity that we have from special and general relativistic theories. So it's another not nice maybe feature of this theory that you have to adopt. It's not only about quantum theory, you have to revise more than that. But I guess the real reason why nobody's doing this, it seems to be very hard to calculate anything with this. And it's just the practical issues, partially, that give the preference to the standard approach and standard calculus. Yeah.
Okay, thank you. So maybe let me add yet another possibility that it has been not touched upon, and that was very popular many years ago, but it doesn't seem to be so popular. And I guess that all of you are not very happy with that. This is the multi-universe interpretation, Everett's interpretation. So what do you think about that? So, or maybe somebody can explain it briefly, for the general public, what it says, and then maybe you can also either support it or criticize it.
No one wants to take it.
You should have invited Arthur.
He was invited. Arthur was invited.
Oh, yeah, Singaporean time doesn't work.
So Ignacio, perhaps you should try to explain it, but I'll point out that I think it is, in this audience, it is not popular. But there are some audiences, for instance, cosmologists and many people in quantum information theory, in fact, it's popular with. So after your explanation, then I'll try to say why I think it's bunk. Is bunk a word that Europeans understand? No?
But we can imagine what it means.
How would a German say it? Is the word scheist?
No, I would never use that word in my life.
Okay, so I give it a try.
So
I
you
will
have
try.
to explain it, Ignacio. If nobody else explains it.
Yeah, I'll do that. I'm very happy. I mean, I'm not an expert, so probably say something that is wrong, but I'm very happy to say that. So there is a seemingly conflict in quantum physics between. I mean, some people say that between the evolution, whenever we don't observe, and what happens when we observe. In some cases, then the evolution is given by some kind of dynamics, some laws of physics, and whenever we observe, then we have to apply another law of physics, which is what is called the projection postulate. And so, I mean, this gives rise to many discussions, and some of the people say that in fact it should not be necessary to have a projection postulate. So what could happen is that we can have that, let's say, an object is at the same time doing two things. So in a superposition, what we call technically a superposition, and then whenever we observe, we don't have to just collapse the superposition and have one outcome. However, the object could be also in a superposition, and then there will be many universes created at the same time whenever there is a collapse, and they are living all together, and the whole let's say there is a wave function of the universe in which we are many superpositions, and in the same way that we are talking here, we are in another universe talking about something else. And this, I mean, according to the practitioners of this multi-universe, then it will have any contradiction with the observations that we have, and on the other hand, would not. We will have a quantum theory in which you don't have to have some postulates for whenever you don't do measurements, and some postulates for whenever we do measurements. So. Is it more or less, Chris? Yeah,
I thought that was quite good. So the universe is always, or the universes, we have to speak in plural here. There's a continuous infinity of Ignacio Sirachs in different worlds, and there's a continuous infinity of Anton Zeilingers in different worlds.
Can just I ask why do you say continuous?
Oh. That's the usual treatment, is that...
It's a technical question anyway, but infinity is okay.
There's an infinity of you that are all slightly different. There's an infinity of me that are different, and some of them drastically different. My difficulty...
Some of them are Bohmians.
Some of them are Bohmians, that's right. And some of them are many worlds, and some of them have ideas like we have. Within that, but so sometimes people say this is too fantastical to be true, and that's not my issue with it. I think a lot of people actually would desire this picture of the world. My friend Charlie Bennett, who's a kind of father of quantum information theory, I think he's attracted to the view from our many discussions. I think he's attracted to the view because it takes away moral responsibility from his life. Well, he can just have fun and do anything he wants because there's another version of him that has done the right thing. And if you listen to many people who defend this many worlds theory, you almost get the sense that it is a religious feeling for so many of them, that they're attracted to it. They would never say so. They would say it's the obvious and only scientific explanation of quantum theory. Many of them would say. If Arthur Eckert had joined us, he would say something like that. But my difficulty is not that. My difficulty is rather that explanation of quantum theory doesn't depend upon any of the details of quantum theory. I can think of loads of ways of modifying quantum theory. For instance, Bohr and Schrödinger discovered that quantum theory crucially depended on complex numbers. you have to have the imaginary number I, the square root of -1 in the theory, or it wouldn't work. But you can make up versions of quantum theory that don't have the imaginary number. They're toy theories. They're not the real thing. But you could give a many worlds explanation of that. You could modify the rules for combining objects in quantum theory to not be something that's technically called the tensor product. And you could still have a many worlds interpretation of that. So my biggest complaint about many worlds is, despite everyone loving it, it has zero content. And I'm not exaggerating. I think it genuinely has zero content and amounts to a religious feeling.
Well, can I add something to that? I mean, years ago, a very famous person from the many worlds camp, I don't mention the name, obtained a very important prize. And I wrote this person an email to tell him that I'm unable to congratulate you, because why should I congratulate you to the fact that you happen, that the person I talked to happens to live in one of the universes where he got the prize, and not in the other universes where he did not get the prize. What's the point? You know. Okay.
Did you ever get the response?
No, I did not get the response.
No, but well, I kind of agree with Chris, but since I'm on a neutral position here, I'm sure that many world proponents believe that the cubists are religious. They just believe that. There are so many theories that will be actually in agreement with cubism. I just mentioned classical and quantum, but imagine some general probabilistic theories. They are very popular. I can make a Bayesian approach to them as well. So what is this? That really, I can tweak many things in probability theories and yet be in agreement with Bayesianism. But I just want to say that I'm not many worlds. And I mean, I give Chris then to respond, but maybe just about many worlds. I feel that kind of there is I find something positive in that, although I don't assume and then do not associate myself to any interpretation as to the truth. But something what positive came out of this is the firm belief that everything and anything could be put in a quantum state. Where the many worlds, I think, makes an error, where they make an error, is in assumption that you can extend, that there is nothing external to that. There is no distinction between the subject, like an observer, and the object of observation. That's where they make an error, and this is not a physical limit. This is an epistemic limit, or a border, or Heisenberg cut, so to say. In order to be even able to speak about something, we don't have no problems with self-reference, and we speak about external things, and then we speak about measurement results, about probabilities, and so on. But nevertheless, we can think of, and that's the core of the Wigner's friend experiment, we can think of having other observers in a quantum superposition, not ourselves, but others. And there is an infinite chain. So I think that probably a very close thinking, close to the many world thinking, brought, after all, Wigner to this Wigner's friend experiment. And this is something which is highly interesting also in our discussion about whose information is quantum state. Is it agent dependent or independent or context dependent, as Alexia would say?
So I want to maybe now shift a little bit the discussion. So I remind you that we have still about 20 minutes, something like that. And so first saying that here they're not representative from many world interpretations, they're not representative from Bayesian theories. We will have another session in which they will be invited and also will be able to criticize your opinions as well.
Yeah, they will shoot us.
Yes. But I wanted to change a little bit the topic and ask you a question that maybe has nothing to do with the topic of tonight, but we did it last time, and I think it was a good idea. Is the question is to each of us, so we go one by one, is so you have not been a quantum scientist or foundational quantum scientist. What would you have liked to be? What is the profession that you would have liked to be? So I would start with Anton. I'm very curious about him. We cannot hear you. You're muted, Anton.
How many possibilities can I list?
Just choose one.
I think many things are interesting in life, and it doesn't have to be science. I'm not sure if I would have had to do with science. There are so many interesting things, like sailing. Sailing is very interesting, or even from a professional point of view, it's quite interesting. Or if I look, I mean, I'm here on the countryside, and I see, and I really like the regulars who all like to do their daily job, and there are so many interesting things. I mean, the guy next door who builds his house, maybe I could have become somebody like that. So I think it's like the many worlds interpretation. I happen to have become a scientist, but this has to do with early childhood experiences and so on. And if they had been different, my God, I don't know what I would have become.
Okay, thank you. Leah?
Yeah, well, I suppose the simplest answer to that is that I'm not really a quantum foundational scientist, and so I've sort of moved from having worked on quantum information to working on philosophy, and so now I do sort of general philosophy of science issues, and I guess I'm just very happy with that. That's actually what I would quite like to be in quite a large range of the possible worlds. So,
thank you. Časlav?
Yeah, I think very early already during my studies back in Belgrade, I somehow felt that I really want to do quantum mechanics and foundational questions. And then I was lucky coming also to Vienna, to Anton, that I could do this. And I'm grateful for this opportunity that I can do it also still. But if it not were quantum mechanics or foundational research, there are certainly other branches of physics that are interesting, but maybe not that many questions that will occupy myself to the extent that I now devote time and passion to quantum mechanics. And so in that case, I would rather do something completely different. My second love was actually film and director of film or anything about film. That was something which I still follow, but that was my kind of a thing that I still love, but maybe don't have that much time to live. Or something maybe almost kind of most simple, like run a cafe or a pub and having some kind of guys that I know that will come every evening. Not many of them, just that we survive. That will be enough. I think I would enjoy that as well.
Alexia?
Yeah, so I will also say I'm very grateful about my job right now. I have lots of freedom to do what I like, and but if it had been different, I wouldn't have minded. Well, there were two options actually. Either going to philosophy, which is something I considered, or completely different, which is acting. I used to act in a theater company, and actually this is this is in the spirit of experiencing different lives and different way of thinking. And this is also what we do in philosophy, actually. We have to embrace different visions of the world. And this experience of tolerance is something extremely interesting. So, well.
Rob?
So when I was an undergrad, I did a joint degree in physics and philosophy because I really loved philosophy as well. And so at the time, I sort of had an appreciation for, you know, what was great about each field. And in philosophy, I felt there was not enough kind of grounding in terms of, you know, what's right and what's not. You know, it's, everything was a bit too much up to debate. And in physics, there was maybe, for the most part, sort of not enough diving into philosophical issues. And so what attracted me to the foundations of quantum mechanics was that it sort of had both those elements, that you could pursue physics and make statements about deep philosophical issues. But at the time, it struck me that I think the field of cognitive science is like that as well. So I was tempted to some extent to become a cognitive scientist. And I think now that we have all this you know, new insight about machine learning, I feel like there's a lot of interesting philosophical questions there about the nature of mind and intelligence that now you can address from the perspective of a scientist. So I think I would have been a cognitive scientist.
Chris?
Oh gosh, compared to all you guys, I'm genuinely dull, because I don't think I could imagine doing anything else. Since maybe the age of 17, I've never wanted to do anything other than what I'm doing. Just a little story. One time when I was working at Bell Labs, I had just moved into a house and I was assembling my bookshelf like the one you see behind me. And a student was visiting the house, and I was working on my bookshelf as he was talking to me. And he said, yeah, and on the bookshelf, there were physics books, there were mathematics books, there were lots of philosophy books. And the student asked me, how do you organize your books? And I said, alphabetical by author. And he said, oh, really? On my bookshelf, I organized them according to the subject. And just as he said that, my wife happened to be walking by the door, and she overheard that, and she said to him, there's only one subject for him. So that one subject is trying to understand what quantum theory is telling us about the world. And more accidentally, I ended up the route of what is now cubism. But I think it was kind of inbuilt. I also like to tell the joke that John Bell, well, I should say I'm one of 5 children, and everyone else in my family is shorter than me, and they have a different facial structure. All my brothers and sisters, and they have a different hair color. Mine used to be blonde. And my brothers and sisters would joke that I wasn't the son of their father. I was the milkman's son. So the milkman would come and deliver the milk, and who knows what would happen. At some point recently, or maybe a couple of years ago, I realized that John Bell discovered his Bell inequality in 1964, which is the same year that I was born. So I've fantasized to myself that maybe John Bell was the milkman, and I didn't have any choice to do anything other than what I'm doing, which is trying to understand the implication of Bell's work for what we understand of reality.
Okay, thank you. So now let me move on to the last subject, or maybe the one before the last.
Just
subject.
a second.
Yep.
Just a second, Ignacio. Can't we ask you also the same question?
Oh, you know, I'll probably will be something like a soccer player or something like that.
The Spanish are very good in soccer.
Yeah. Yes. So actually, I wanted to come now to some, I mean, down to earth, let's say, if one can say that, a question, which is experiments. So do you think that what we have been talking about, is there any connection to experiments, or is there any hope that experiments can give us a hint? Or put in other words, imagine that now you have a wonderful experiment that has an infinite precision, so it gets as precise as you want. So do you think that this could serve us to decide, or to maybe to have a conversation in a different direction that we have now? Or we are talking only about philosophy, some discussions about interpretation? It's a little bit more like taste or opinions. So I wanted to start with Anton. What do you think about that?
Well, this is a very good question. I mean, I'm thinking back. I'm doing these experiments now. Now it's really nearly 50 years. It's amazing how time flies. And I remember when I gave my first talks, for example, on our precision two-slit experiment with neutrons, where we really showed that the interference pattern builds one by one and so on. And I gave talks at famous universities, and afterwards famous professors walked up to me and said, it's really that way? It really works for individual particles? And I told them, I mean, what else did you expect? And what has happened to all these due to these experiments is firstly that the foundational issues have been taken much more serious than before. And this is very important because it opened up the mind for new basic questions. It allowed us, for example, the discussion which we had today would have been impossible 50 years ago or even 30 years ago. This is a huge progress. And secondly, the whole thing opened up also the technological possibilities of quantum information and so on, because people's minds were open. People suddenly realized, we can do this, we can do that, we can combine all this and so on. And I'm sure that this development will continue. And I'm certain that there will be new experiments on foundational questions. Actually, right now, I worry a little bit with all the developments going into quantum information, quantum computation. The experimental side of foundations is probably not getting the weight any now which it should get. But that's my personal opinion.
Thank you. So what the other people think? Rob?
I can weigh in, yeah. Maybe I'll say something general that one often hears, at least I often hear this notion that, well, maybe an interpretation of quantum mechanics is just something that you sort of add on, just a story that goes along with the formalism, but that there's essentially, that it doesn't have any experimental relevance in the sense that, whatever story you add on to the formalism, the kinds of predictions you're going to make are going to be the same. And I want to push back against that kind of notion that interpretations are somehow inert. That ultimately we're not in the business of just making predictions about some pre-existing set of things that we've decided we're going to do. I mean, we ask questions like, what's the next interesting experiment to do? What might be useful as a strategy for doing something interesting, building a new technology. So to some extent, your interpretation, your point of view on quantum theory dictates, what you do next, and what sort of experiments are you going to try? What are you going to try to make predictions about? And I think it's just not the case that people who have different views about the nature of quantum theory all have the same assessment about what we ought to do next and what might be interesting, what might come out and be surprising. And I don't think quantum theory it's not a done deal. It's not a monolithic thing that's given to us and is fixed and is not going to change anymore. That, for example, just in recent years, people ask questions like, what's the quantum analog of, say, machine learning, or a field known as causal inference or causal modeling, or computational models. All these things, depending on your views of quantum theory, you're going to approach those questions differently. It's going to lead you to different ideas about what sorts of, experiments to do. And in my view, we've been seeing more and more interesting new types of experiments because of people's different views on how to think about quantum theory.
Well, I think we'll have to fight for that. And so it's in the direction of what Anton was saying at the end of his speech. This boom that we have on quantum technologies right now, so it's a good thing for people who do quantum, but at the same time, we need to pay attention, to be very careful. All this does not become only engineering. We still need to keep vivid the quantum foundation part, the philosophical question, and to make a point that it is important we still dig on the fact that we still don't really know which reality we are talking about. And this deserves experiment. So now, will there be a discriminating experiment that will tell us which interpretation is right or not? This, I really have no idea. But I think it is important that we still keep putting money on this kind of question, because we are also here to understand the world and not only exploiting nature. And that's not the spirit these days. So
Thank you.
I share this. Sorry.
Yeah. Oh, no. So maybe you can, since we have just a couple of minutes or 5 minutes, I wanted to ask something to Leah that I'm very curious about. So what do you think that quantum physics can do for philosophy, and what can philosophy do for quantum physics?
Well, maybe I'll go with the second one first. So I think what philosophy can do for this field of quantum interpretations is sort of set different options for the playing field that we have to start with. So, I mean, one of the things that's come up in this discussion is, should we take the quantum state to be representing a piece of reality or not? And I think there are sort of general philosophical programs which motivate the kind of view that we should expect things in a theory to be representational. But there are other philosophical programs, like, for example, American pragmatism. That's why I'm attracted to it as Chris is, which don't take that starting point at all, which take a starting point where you have an agent central. It's sort of like, if you act in this way, then you get this outcome. And so I think that one thing it can do is to sort of help us to see that there are sort of presuppositions behind different interpretations in terms of their sort of philosophical starting point, and perhaps sort of open the space for other possibilities. And what can this stuff do for philosophy? Well, I mean, I think that some of the things that threaten to come out of quantum foundations. For example, people consider the idea that we need to revise the notion of probability or causation or inference. And those are very interesting things. And if those would turn out to be, something that really took hold, then that would be like, those would be major philosophical results.
Okay, thank you. So I have some provocative question that actually was written in the chat that I would like to ask you, and so maybe we can start finishing the conversation with that. So it's what do we understand now about the measurement problem, but I would put it more broadly about, let's say, quantum foundations that von Neumann did not understand back in the 1930s?
I'm not sure if von Neumann understood it in 1930.
That's a very good answer. Yes. So I think that there are many things that we can say, but I mean, just
on occasion, I've tried to mimic William James, who talked about rationalism being the great original sin of something. I think that von Neumann's analysis of measurement in 1930 was the great original sin that cast physicists out of Eden and led to this continuing quantum debate. So I don't know if for myself, I think it was the realization that his analysis was just didn't make sense from my point of view. So I've learned that, but maybe I've only learned that personally.
Let me jump in. If you ask the same question about Einstein, you know, what Einstein famously in the Einstein-Bohr debate sort of talked about, basically he saw no reason, no facts that would incline him to think that, you know, quantum theory had to be a complete description of reality. So roughly speaking, there wasn't anything there in Einstein's mind that really showed that some hidden variable explanation, for example, where the quantum state was an incomplete description, you know, was problematic at all. Now, there was von Neumann's no-go result, which Einstein didn't really comment on. But in that time, you know, in the 60s, we got the quotient spectra theorem that Anton mentioned and Bell's theorem. And they're the things that I think it is appropriate to point at and say, those are the facts that are hard to explain in the kind of program that Einstein had in mind. Those are the things that really force us to acknowledge that a quantum world requires you to innovate in a dramatic way. You know, maybe your notion about what a causal theory is, maybe your notion about what a theory of inference is. But you can't sort of be complacent. And that's a huge difference relative to the 30s, in my view.
Maybe I can just add that I think that we still do not understand fully what is called as a measurement problem, and maybe other disagrees with it. But so we all learn during studies about this kind of continuous evolution, Schrödinger equation, and abrupt change of quantum states upon measurement. And imagine that you never had a lab course, and you just learn this from the textbook. And then your first day in the lab course, your first time in front of your optical table. And somebody take your finger, put on an element and say, okay, now as a theoretician, would you apply one or the other rule? You would not know that. We cannot learn that. There is nothing in the book about that. It's through our experience that some things click, like the detector, and say, oh, now I project. And the others do not click, or we don't see them, or don't hear, but they do. So there is a certain ambiguity there. We are kind of understanding the extreme cases, but not fully. I'm not saying that that's a real problem of a theory. I just want to say that we haven't learned fully how to make this, to resolve this ambiguity. You're muted, Vanessa.
Thanks. Very good. I think that the time is now up, so we have to finish. So if there is any, let's say, one sentence message that you want to send for, it's a summary or some message that you want to say, just say it now, or otherwise we will conclude.
One very brief sentence. I mean, even as I have my favorite interpretation, it is important that people have different interpretations, because we do not know where the past leads into the future, and this might be completely unforeseen.
And I'd just like to maybe add that the reasons that I have for thinking that the moon is there when no one's looking have got nothing to do with quantum mechanics at all.
Very good. I think that that's a very good statement to finish this discussion. So with that, I mean, let me just, before concluding, maybe let me tell you that we will have another session of this Munich Quantum Stammtisch. This will happen in a month. So the subject is not yet decided, but stay tuned and will be posted in our webpage. So let me now conclude. just by thanking our guests for bringing their expertise and experience around the table and engaging in such fruitful, constructive, and open exchange throughout the last 1.5 hours. And I would also like to thank Anka Ionescu and Tatiana Will. They are from MCQST for preparing everything, organizing, and sending some beverages to the speakers. I know that some of them didn't receive them yet, but probably will receive it soon. So thank you very much, and stay tuned. Bye-bye.